Hi, everybody. Good morning. Thank you for joining us on this Sunday morning. I'm sure it was difficult. We're going to talk about Crypton Exposing malware's deepest secrets, which describes a research we recently conducted, Anna and myself. And the output of this research was a tool that extracts decrypted content from malware. So a little bit about myself. My name is Julia, and I'm a malware researcher at the F5 security research team. I've been analyzing financial malware since 2012. My colleague here is Anna. She's been on my team for quite a while, but recently she left us, very sadly. And she's also a software engineer, in addition to being a reverse engineer. So lately on the news, everybody's been talking about ransomware, like WannaCry. Ransomware attacks are very famous because many people choose to pay, and we can see that in the revenue. The estimated revenue for WannaCry is $55,000. For CryptoWall, which is a little older malware, $18 million, and CryptoLocker, $30 million. This is for the ransomware industry. But the estimated revenues for the financial malware industry, as you can see, are, for example, NeverQuest, $5 million, Drydex, $50 million. Zeus Game Over, the highest revenue for financial malware, $100 million. So as you can see, the revenues are higher when we're talking about financial malware. One of the reasons for this is that in ransomware, you can choose whether to pay or not after the malware is installed. But it's financial malware, you don't really have a choice. Once your credentials are stolen, the malware will commit its fraud and steal your money. So this guy, we took it off the most wanted list of the FBI. He's responsible for Game Over Zeus, as well as CryptoLocker, and there's a $3 million reward for any details leading to his arrest. So if you see him here in the audience, please raise your hand. It's a lot of money. So what we're going to talk about today, we're going to give you a short background on financial malware in order to make sure that we are all on the same page. Afterwards, we will describe the problem we encountered and the solution we chose to use as the appropriate solution for this problem. So as we said before, the purpose of financial malware is stealing credentials and other useful information to commit fraudulent transactions. That's why they have to reside in the browser's memory. So once the malware is installed on the user's machine, it injects its code into the browser and runs in the browser context. And then it installs function hooks on network APIs, such as HTTP send requests. It does so in order to intercept and modify outgoing requests and incoming responses. And as we said, eventually the goal is to steal credentials. So how does the malware knows which URLs it should intercept? It has WebInject's configuration. It's a malware configuration which tells the malware which banking sites to target and also which JavaScript code to inject into the banking page. This JavaScript code can also perform automatic transaction, saving time for the fraudster, maybe for the user. And this is an example from TeenBuzz WebInject's configuration. As you can see, the first line is set URL, which indicates the targeted banking site. Later on, you can see the JavaScript injection. Here, it fetches external scripts to be run in the context of the DOM. And later on, it deletes all of the objects in the JavaScript it just created to avoid detection by different security vendors. Another malware configuration in the financial malware world is redirects. Redirects are a little bit different from WebInjects. They're also called server-side WebInjects because what happens is the requests for the banking page are intercepted inside the hook. Afterwards, they're redirected to the malicious server, which in response returns a fake banking page instead of a real login page. This is a common method used by TrickBot malware, Drydex, NeverQuest, GoodKit, and other forms of malware. In this diagram, we can see that what happens first is that the infected user machine sends a request to the bank, and the communication is established, but also inside the socket hook, another request is sent to the malicious CNC, which returns a fake login page. The content of this fake login page is used instead of the content of the real banking page, meaning that it's nothing like phishing because you can see the URL of the real bank and the certificate is still the legitimate certificate of the real bank. Only the content has changed. This is an example from a redirect configuration of TrickBot malware. The first line is also the targeted bank, and the last line is the IP of the malicious server that is going to serve the fake banking page. The string that you see here in orange means it's actually a header that's added to the request for the malicious server, which indicates which banking page to return to the user. So how does this configuration we discussed ends up inside the browser's memory? Well, first, after the malware is installed, it receives the configuration in encrypted form from the malicious CNC. It's stored somewhere on the infected machine. It can be in the registry, it can be as a file, it can be in the shared memory, and at some point, it's going to be decrypted. But before analyzing the malware, we don't know when this is going to happen or in which process. Once it's decrypted, it's utilized inside the network hooks in the browser.
So one of our main goals at our jobs is to extract the configuration in order to investigate its man in the browser logic and to update our company product. But this can become a complicated goal since the malware writers invest endless efforts into hiding its secrets. So in our company, like other security vendors, we have a sandbox automation to extract malware configurations. And before Crypton, the product of our daily research used to be specific decryptor for each malware type. This decryptor was used as input to the automation within the malware sample. And this automation purpose was to execute the malware within the decryption script, and the output expected to be the decrypted malware configuration. So while conducting the research for the sandbox decryption automation, we face the following challenges on a daily basis. So for each malware, we have to answer, where is the configuration stored? We need to locate the configuration right after it has been received from the malicious server. Then what encryption stages occur? Encryption may consist of several encryption and decompression stages, and these stages might be spread over the number of processes. So the next challenge is find out if there is a custom crypto algorithm. If not, we can use the existing implementations in our script. In the case it was customized, additional research required to reconstruct the scheme and the changes that was made. So when we have identified the algorithm, the missing details are the encryption keys, and we have to find a way to extract them. In some cases, the key can be located right next to the configuration inside the memory, while in other cases, it may be hidden in a totally different location in the infected system. And the main problem for us is that all above changes frequently and also changes per variant. So here is a snippet from some Twitter conversation. Malware tech researcher tweets, I'm writing config decryptor again. And then someone that presents himself as a Dridex bot answers him, no problem, we will change the encryption algorithm. Now it can be done by click on the button in the admin panel. So this short conversation shows to us that the issue became an inside joke among the malware researchers and the fraudsters as well. But the sad truth is that each malware click can make us as researchers work for weeks. So what does it mean for us? It means that our job routine consists of reverse engineering the sample, the malware, find its crypto algorithm, and then find the encryption key. Then you write the configurations and decryption script and repeat it in an endless loop every day and all life, like reverse, decrypt, repeat, reverse, decrypt, repeat every day. Oh my God. So we have to stop this madness. And it's obvious that the issue of writing decryptors demands more fitting and better solution. And while dealing with applying again and again the same procedures, we start wondering about how this process can be automated. So before writing tons of code by ourselves, we try to find existing approaches for generic identification on crypto that already exist. And as a result of our investigations, we can divide the solution that we found into two main groups. First group is the plugins for static and for dynamic analysis, like iDecrypt. The majority of reverse engineers are familiar with these tools. These tools are very convenient for usage and actually very efficient and extremely helpful for the manual reverse engineering process. But the main problems for us while using them was the fact that they based on identifying specific signatures and constant values inside algorithms. So this will not identify a custom crypto implementation inside our malware. The other group is in academic approaches. These approaches try to handle the decryption process in a more generic and unique ways. For example, by inspecting the entropy of data inside the buffer, or the input-output data relationship inside these buffers. But unfortunately, we found that the existing approaches also not useful in the case of custom algorithms. So after the conclusion that we have to implement the unique solutions for our need by ourselves, we've proceeded to find our approach. Our approach based on the assumption that at some point in time, malware will decrypt the configuration by itself. So we only need to be there when it happens and dump the decrypted data. So what exactly do we want from our solution? We want to identify any cryptographic algorithm, regardless of its type. We also want to follow the propagation of the malware inside the system, since the decryption may occur at any point, and we want to dump the decrypted content at that time because this memory might be overwritten later on.
So introducing Crypton, which is our idea of how to handle this situation. First, we asked ourselves, what do all crypto code blocks have in common? Does anybody have an idea? Okay, great. That's a great answer. So, not only XOR is used, but here we can see implementation of AES and RC4. When we look at them, we don't really see anything in common. But when we dive into assembly, they're still not identical, but we can see some resemblance. We can see that both of them have loops, and inside those loops, there are XOR operation, as well as other mathematical operations like shift right, shift left, multiply, or divide. So our idea is to find loops with mathematical operations in them, and that's how we decide which code blocks are actually cryptographic code blocks. So now that we know what we are looking for, we're asking ourselves, where should we look for it? So we had several approaches that we've considered. For example, tracing all the buffers from Windows I/O APIs. For example, create file, or if we're talking about sockets, then send and receive. But then we came to the conclusion that if we enumerate all of those functions, we'll get to a huge function subset, as well as the fact that we need to update this function subset once new APIs are released, especially customized APIs that each browser has. And once Windows updates its DLLs, we also need to update our API. So we decided not to go with that idea. Another approach we've considered and implemented was following memory allocation accesses. We put page guards on allocation that we think, on all allocations actually, and once the breakpoint is triggered from the page guard, we inspect the code that triggered this page guard and see if it has cryptographic code blocks in it. But once we implemented this, we realized that during I/O operations on these buffers, there were problems because it proved to be a bit problematic because I/O accesses are volatile. And we also encountered race conditions in multi-threaded environments. So we decided not to go with that approach as well. So the approach we did choose eventually was to statically traverse the code. This means that before the executable code is actually executed, we inspect that region of code. We scan the code and look for loops and mathematical opcodes within those loops. We generate a cryptographic score for each function containing those loops and check if it's above a certain threshold. This threshold actually helps us to adjust our algorithm so that we don't have false positives. And if the cryptographic score is indeed above the threshold, we put a breakpoint in the beginning and at the end of the crypto loop. So now that I've mentioned breakpoints, our implementation involves a debugger, a scriptable debugger framework named WinUpDBG, which is entirely in Python. This is how we implemented the tool. So we want to follow crypto loop execution, as we said. We put a breakpoint in the beginning and at the end. We want to store all the allocated pages in heaps, because once we hit the first breakpoint of the loop, we want to calculate the hash on all of those buffers. Also, at the end of the loop, we want to calculate this hash and compare it. If we see that there was a change in the hash, it means the buffer changed during the cryptographic loop. Then we'll check the buffer for plain text. And if we found the plain text, we say yay and dump it because we assume this is the configuration. Let's review this in a diagram form. There's an executable region that we inspect. We scan all of it, and we put breakpoints on allocations and on cryptographic loops. So several allocations are created. We store them all, data allocations. And when we reach the breakpoint at the beginning of the XOR, we calculate a hash for each such buffer. At the end, we calculate a hash again, and we see for the last buffer that the hash has changed. So we inspect that buffer for plain text. And if we have plain text, that means we got the config that we wanted. All this would be great in an ideal world, but we need to deal with real live malware. So there are other factors that we have to take into consideration, and Alan will describe them now.
So what Julia described until now was the Crypton core that identifies crypto blocks and how and where. But now we're going to discuss how it fits into a malware's propagation flow inside the system. In real life, we don't know which process is going to decrypt the data. The malware's propagation flow starts from the very first exe file, which injects itself into common system processes like SVCOst or Explorer, or create additional processes for itself. And then while the user opens one of the browsers, these malicious injections are ready to propagate themselves into the browsers as well. And once injected, this code will actually launch the man in the browser logic for the targets that defined inside its configuration. So since the decryption may occur inside any of these processes, we have to attach Crypton to each one of them. And we do this by hooking functions like anti-resume thread, which transfers the execution from one process to another. So far the encryption process in a diagram, we have the Crypton core applied to the first malicious exe and then propagated by attaching itself to all the infected processes. Another challenge we have to take into account is packed malware. We want to apply the static analysis to the unpacked code, and we want to make this traversal before any unpacked code was executed. So before dealing with unpacking in a generic way, we were using a malware type specific method to find the code entry point. But if we want to automate this process, we have to face the unpacking challenge that is considered to be very complex. So we've decided, instead of approaching it, to bypass it. Instead of trying to find the entry point of the malware and then apply the crypto core, which is a difficult problem, we will apply the Crypton to all the new allocated regions. So in order to find when the execution passed to the new region, we will follow all the branches of the code execution flow, for example, calls and jumps instructions and other ways of passing the control flow to the new allocated execution region, and then apply our Crypton core on them. So in this way, eventually the Crypton will be applied to the main malware code. So here's an example of malware that starts from packer entry point address and creates additional payloads during its execution. We attach Crypton code to each one of these sections. So eventually the final payload will allocate its RW buffers that we would like to inspect inside our crypto loops breakpoints. So now we come to the point of summarizing all the flow until now. We scan all the executable regions to deal with unpacking. On each executable region, we apply static code analysis to find crypto loops and place breakpoints on them for later dynamic analysis. We intercept allocation-related APIs to store buffers for the later inspection. And then, as a part of dynamic analysis, when crypto loop breakpoint triggers, we compare the buffer stages that we stored before. If the buffer was changed and contains the plain text, we dump the output, and that's good. So eventually we handle all the process injection flow in order to apply all the logic for any process that was infected inside the system as well. And in the diagram, as you can see, the first REcon section, which is a packer, starts to be executed. We traverse its code as a part of our traversal Crypton logic and handle all the allocations APIs and ways to pass the execution flow to the different region, like jump EX, here is an example. And then the packer allocates the new regions and writes its next payload to its regions. And crypto identifies inside the triggered breakpoint that the execution flow is going to be passed to the new payload within the jump instruction. So we apply Crypton core on new allocated payload before it starts to be executed, which in this example is the final payload actually. And then the Crypton core inspects the inner allocations and crypto, finally extracting the payload as we saw before. By looking at the bigger picture, we apply all this logic for all the infected processes inside the system.
Okay, thank you. So before we show our demo, we want to show you how it looks like from a reverse engineer's perspective when you have to do this manually. We used TrickBot malware. Great. Searching for the config in the browser. Static analysis of the malware browser module.
The timer is in hours, actually.
The config leads to pipe communication, which leads to the malware's model and SVC host exe, which we also need to analyze. Analysis leads to the parent process, the malware exe, unpacking the malware's code. Takes 4 hours. Static analysis of the unpacked code of the malware. Debugging the malware with the decryption routine. Here we can see the decrypted configuration after it was decrypted by the decryption routine and not just found inside a memory of a process. It took 24 hours without lunch and without sleep. So,
and without writing the decryption script, actually.
So now we want to do it with Crypton and hope that he does the job for us. Starting to run, you can see the log over here. I'm expecting to see the output of the decrypted content in this out folder right here. Let's look at what the tool actually does. You can see that we execute the sample with Crypton. This is the malware sample. We start the execution from the entry point of the malware, which is actually the packed code. It's not the real malware code. So we need to inspect each executable region for cryptographic code, and eventually we hope that one of these executable regions will be the unpacked code of the malware. We can also see that there's a code override right here. It means that packed malware, they often do that. They override their own executable code with a different payload. So we need to take off our breakpoints from this region in order to inspect it again with static traversal. We want to store buffers, buffer allocations. We also want to store heap allocations. In some cases, we can see that malware uses APIs such as is debugger present in order to make the researcher's life a lot harder, but we patch this, so we return 0 for this malware. And later on, we'll see that once it sees a crypto loop, it will calculate the hashes. And once it calculates the hashes and compares them, we'll be able to see the outputted decrypted configuration right here. This is the decrypted content from one of the configurations of the malware, which we extracted. And when we use Crypton, we don't really need to reverse all the decryption routines. We just use it and get the decrypted configuration. So here, you see these hashes. Before the end of the crypto loop, it calculates the hashes, and after the end, it sees that it checks it for plain text, and if it has plain text, it will dump the configuration that you've just seen. Okay. So we'd like to discuss the research results that we got from using our tool. First, let's talk a little bit about performance. It has a minor execution time toll because we do go over all the code. So it depends on the code length for the static traversal, and also on the point in time where the malware decides to decrypt the configuration. So for example, if the malware was to sleep for 10 minutes, obviously we will get the decrypted configuration in a little over 10 minutes. Regarding false positives, we mentioned thresholds. So we use the cryptographic score threshold and also the ASCII and Unicode threshold that we can adjust in order to avoid false positives. We applied Crypton to all of the following malware: Ramnit, TrickBot, Atmos malware, Kakbot, and Tinba, which are common financial malware. As you can see, they use different cryptographic schemes. They use decompression such as UCL and uplib and LSMAT, and also encryption such as AES and RC4, and it successfully decrypted all of them automatically. So after we realized this, we now know that we don't have to work ever again. So finally, the additional applications we thought of for Crypton. We actually use some of them. It can be used to extract encrypted strings from malware and encrypted APIs, as well as domains from domain generation algorithms. Use this for Tinba malware. And regarding ransomware, it might be possible to use Crypton in order to identify file encryption, because we already put the breakpoints on the encryption function in the beginning and at the end. And we're not interested in ASCII checks because file formats contain different information, not only plain text. So we can compare entropy in the beginning of the function and at the end and see if it's increased, and then decide that it was an encryption by ransomware. So thank you very much.
So as far as I can understand, you detect once the config has been encrypted by checking for some strings or ASCII text. But have you seen any malware that does not decrypt config at once and maybe keeps it encrypted and decrypts chunk by chunk, something like that?
Yes, we have seen that, and it works for that as well. We adjusted the algorithm to work for those cases as well.
Okay, thanks.
So I've noticed that all of the malware that you've been demonstrating here uses text-based configurations. Have you found any malware that uses like protobuf or any of the other sort of structured binary formats, and does your tool work with them?
So there are some, when you talk about financial malware, eventually you need to have the string of the URL, but what you said is correct, because some malware do use binary flags inside the configuration. You still can get this with the tool by adjusting the ASCII threshold. If you allow to have some binary content, not all ASCII, then you're allowing for configurations such as the one you discussed.
Hi, Alson Talk. I'm probably pretty sure that the tool does, but in the SAC example about REbug, when you do the demo, maybe it's because the panel is not active, but it didn't get the web in yet. So it's like a loop, right?
Yeah, it just took a couple of more minutes, so I skipped it, but I can show you that it...
Maybe we can see it now.
Yeah, I can show you it now, because now it already got the...
No, but I mean
that
if you continue hooking, if you wait...
Yeah, actually, the rest of the configuration here in the biggest file.
This one.
Yeah.
Yes. The configuration.
Yep. It's there.
Okay.
Thanks.
A great question.
Very excellent presentation.
Thanks.
I had a question. Do you have any plans to make Crypton a publicly available tool by other security researchers, or is it going to be proprietary technology by your company?
So great question, because at the moment we're dealing with the legal department because we want to make it available, and we hope to make
some parts of it.
At least some parts of it will be made available, and we're working on making all of it available.
Awesome. Thank you so much.
Thank you.
So can you talk a little bit more about how you score your functions that you think are crypt-related? Are you just counting the number of specific instructions, or do you have another method?
We have to, we actually do calculate the score by the number of instructions, but it depends on also in some inner loops that exist, or some of actually, if one of the instructions exists and then a number of other instructions, we make the score higher, and that's how we can adjust it to the existing implementations.
And have you sort of gone back and refined how you're scoring based on the type of implementations you're seeing, or you're not changing that part right now?
We're not changing it, but mostly we use the threshold for finer tuning.
Yeah, if we found some malware that our code doesn't work on it, so we obviously have to change something, but so far it worked.
It sounds simple, but it works.
You said that you patched is debugger present. Have you considered patching other things like timing, things like that, so it runs faster?
Yeah, it's a great idea. We implemented some of this logic, but we probably implement more.
Actually, we have to consider all the anti-debugging techniques in order to make it work on our code.
That's it. Thank you.